So now that we've discussed looking at initial conditions in an RLC circuit, which is going to be problematic probably for some people, let's go on and discuss the source-free RLC circuit. So there's a picture of one with a resistor, an inductor, and a capacitor right here. This is a really, really important circuit, and we will spend time with aspects of this circuit for the rest of this textbook. So understanding the frequencies and the properties of it will be very important. It's an important circuit for filter design. We will do lots of filter design, and it's an important circuit in communication networks. So let's work on it. So this is the circuit in question. Right now we'll start with the series RLC circuit. So series circuits we usually analyze with KVL. So if you're analyzing with KVL around the loop, we're going to have voltage in the resistor plus voltage in the inductor plus voltage in the capacitor equals 0 because I have no sources in here, correct? So voltage in the resistor, when we only have one current, right? Because Kirchhoff's law says we only have one current. But we also have some initial conditions here. So we have an initial current from this inductor, and we have an initial voltage across this capacitor. So those are our initial conditions. So KVL, we want KVL. We can write this one okay. I times R, only one I in there, right? And we can write the voltage on the inductor pretty well because we know that that's L di dt. But voltage on the capacitor, we have a little bit of an issue because right now we have an equation for current on the capacitor, which is I equals C dV dt, correct? So, but we want the voltage on the capacitor right here. So we need this voltage right here that's hidden, embedded in this differential right here. So what we can do is integrate both sides of the equation. We'll integrate from negative infinity to 0 minus. Same thing on this side. If you integrate the left, you have to integrate the right. So we'll do that. So we'll integrate both sides. We rewrite this a little bit. So I dt equals integral C on the outside of 1 dV, right? Okay, so now we can go ahead and integrate. Well, let's divide both sides by C, and we have 1 over C integral from minus infinity to there of I dt equals V in the capacitor at time 0 minus plus, or minus V in the capacitor at time negative infinity, because I'm just integrating a 1, which means it's going to be a V, a constant, right? So we assume that the charge initially on the capacitor at negative infinity is 0. So at time negative infinity we have no charge on the capacitor, and so we come up then with that the V in the capacitor at time 0 minus equals, we'll just say that's the initial V, which is right, that's what we have, the initial V, and that equals 1 over C, this integral I dt. So now I have an expression for voltage on the capacitor that I can put into here, into my equation. Okay, so now we have KVL written for this series RLC circuit, but you see it has a derivative in it and it has an integral in it both. So the question is, what are we going to do with it? So the way you handle that is to go ahead and take the derivative of both sides of this, or take the derivative again of all of this. So no reason why I can't say d dt of everything here. And when I do that, I get, oh, and I'm also going to divide everything by L just to clean this up a little bit. So when I do that, I'll get di dt of R over L plus 1 over LC I plus di squared dt squared equals 0. So this is the equation that we need to find a solution for. So I'll just move that to the next slide. So this is a solution we want to find a solution for, and we learned in the last chapter that a differential equation, a first order differential equation, had a solution of the form, generic form, that was a solution. So that's a good place to start. And actually, if we put this assumed solution into this equation, because we know that we have a feeling that the first derivative, a linear combination of this plus the first derivative of this plus the second derivative of this will still be an e to the st function. So that gives us a warm feeling that this is possibly a good solution. So we'll do, so di then dt will equal a s e to the st, and the second derivative of that will still equal a, but s squared e to the st. And so you put that back into this equation right here, and we'll have, and I'm going to put the second derivative first, so I have a s squared e to the st plus, yes, plus r over l a s e to the st plus 1 over LC a e to the st equals 0. So I found those derivatives, I substituted it back up into this second order differential equation, and that's what it looks like. Remember, we're trying to find our solution for the current I that solves this differential equation. So so when I do that, I see that the a's cancel out, the e's to the st cancel out, and I'm left with s squared plus r over l s plus 1 over LC equals 0. This is a quadratic equation in S. So I'm just going to clip that over for you. This is a quadratic equation in S that is going to have two roots. The roots are going to be actually in your textbook, the roots of this equation. Just clipping it over here so I don't. So this will be the two roots, and they're called S1 and S2 in your textbook, which is fine. We can rewrite those a little bit because this is a little bit of a ugly formula, if you will. And if we rewrite that a little bit, because it's going to be convenient for us going forward, we can actually say that this is minus alpha plus square root of alpha squared plus, and this is going to have meaning in a bit, omega naught squared. So that's S1, and S2 we can also rewrite as a minus alpha minus square root of alpha squared minus omega naught squared, where alpha is r over 2l, and so there's alpha squared, and omega naught is actually defined as 1 over the square root of LC. And this is going to make it easier for us to make these substitutions and make some observations about the circuit behavior as a function of what these values of R, L, and C are, and the initial conditions on the circuit. Sometimes also, I'm going to mention here, it doesn't show it in your textbook, but it can be convenient for us. Sometimes that's written as minus alpha plus a beta, and a down here would be a minus alpha minus beta. So sometimes the form of that equation is also convenient. So we have these two roots right now, and we said that our solution for the current is going to be in the form of a e to the st, but we have an s1 and an s2. We have two different roots to this equation. So in reality, our solution is in the form of, there's no reason why it can't be a solution of the form, because they're linear combinations, I1 plus I2, or I2. So the final current is actually a linear combination of the current associated with one of the roots to that equation, because they're both solutions, right? Plus the current associated with the other root of the equation. So the final solution to our not final because we haven't put the initial conditions in, is going to be an A1 e to the S1 t plus an A2 e to the S2 t. So this is the total current, the total solution to that second order differential equation, but we have not yet determined these values of A1 and A2. So part of the way that those values are determined, those are from the initial conditions in the circuit, and since we have two roots in this equation, it's going to require two initial conditions, because we have found S1 and S2, but we have an A1 and an A2 constant still to determine. So that's two unknowns. That means we're going to have to need two initial conditions to find the values of two unknowns. So we have an initial condition I0 on the inductor, and we have an initial condition V0 on the capacitor. I and V are related through a differential equation, but we need initial conditions on I, because our second order differential equation is an equation in I. So what we really need is we need an I at time 0 or 0 plus, and we need a di dt at time 0 plus to apply to our differential equation. So we have this one, it's equal to I0. The question is, do we have the other initial condition for that differential equation, second order differential equation in I? And we can get that. So going back to our original differential equation and putting in an initial condition at time 0, which is where we are looking at, or 0 plus, where we're looking at the behavior of this circuit. So we can have this plus L di at time 0 plus dt plus our initial voltage here equals 0. So this is our KVL written again, but at t equals 0 plus. So the instant we're looking at the response of this circuit. So I've put initial conditions in here. So we come up then with, we want to solve for this part right here. So we have L di dt equals minus R I minus V0. And so di dt equals minus 1 over L R. And what is our initial current? It's I0 minus VO. So this is one initial condition right here. Ooh, it's so hard to draw on this drawing pad sometimes. And here's our other initial condition right here. And so we will use those initial conditions in the circuit to find what you do is you substitute the assumed this solution back into the second order differential equation, and then you apply these known initial conditions to it, and you'll solve for A1 and A2. It's a little ugly to do all of that math, but it's actually nicer at this point to consider some separate conditions in this circuit, so some different scenarios in the circuit. So if I look back at what these two roots are right here, the two roots to this equation are here and here. And there's several conditions that can occur that depend on the values of the R, L, and C. In one case, we could have that, well, this is going to always be a real number here. This will always be a real number. This is always a real number. But this part may not always be a real number. So this number, if this number is a real number, then root S1 is real and positive. If this number equals this number, then we have a root to 0, right? And this would be 2 alpha down here. And then we have another case where this number could be negative under the radical sign, and in which case your root is a complex number root. So it's an alpha plus j something over here, or I. So let's talk about that little thing here for a moment. So this is an odd thing, but it has to be said. So you probably took a math course where you found out that the square root of -1 equals I. So an imaginary number I. Well, you can see that in engineering we are using I's all over the place for current. So in engineering, I is a current, right? So in engineering, oftentimes, and we are going to do that here, we are going to define the square root of -1 as a j. So I won't be using I for a complex number in here. I'll be using j so that we don't confuse the I's and I's with the I's that mean current. So that's going to be the convention going forward, and it's the convention in electrical engineering to say the square root of -1 is j. So that makes for all kinds of jokes between engineers and physicists. So more on that later. So I'm going to look at the three cases of the three different, go back one here, so actually go back to whether this gives you the answer of 0, or gives you a real number, or gives you a complex number. So in remembering, I also, these are our initial conditions that we can subject to the problem. So there's three cases. So when the alpha is greater than the omega 0, we call this the overdamped case. When they're equal, it's critically damped, and when alpha is less than omega 0, we say that's underdamped case. So how the circuit behaves falls into these three different categories, which we're going to look at each case individually. So let's look at the first case, the overdamped case first. So prior to doing that, we should look a little bit more at how I get the solution, because I'm going to give you examples and plots with real numbers that aren't in the textbook. So the first thing is that we had the current. The solution for our current was A1 e to the S1t plus A2 e to the S2t, and we found out what A1 or S1 and S2 are. So we want to start with applying to the initial conditions, which are at t equals 0. It's actually 0 plus or 0 minus what happens in the circuit. So we do have that I at 0 equals I0, and we know that I'm going to go ahead and put 0 in for our equation right here. So that's A1 e to the S1 times 0 plus A2 e to the S2 times 0. So that's A1 plus A2. So I said we need two equations to figure out what, two initial conditions to figure out what A1 and A2 are. So these are one of our equations. And our other one, we're going to take di dt. And we know what I of t is. It's right here. We take di dt of it. But also, well, we're going to take di dt of that, but we're going to set it equal to what we determined that to be. So that was minus 1 over L R I0 plus V0, which equals so that is taking the derivative right here, we get A1 S1 e to the S1t. We already know what S1 is, plus A2 S2 e to the S2t. And so we have that equated together, but we have it at t equals 0. So then we have that, this part still the same, equal to A1 S1 plus A2 S2, and we already know we had our shorthand notation of S1 equals minus alpha plus beta, and our other shorter notation was that S2 is minus alpha minus beta. So minus 1 over L R I0 plus V0 equals A1 minus alpha plus beta. Remembering that these alphas and betas are functions of R, L, and C, plus A2 minus alpha minus beta. So what we have here is two equations and two unknowns. That's the first one. That's the second one, with our two unknowns being A1 and A2. And so you can go through all of that tedious algebra, which your book doesn't do, and neither does my second reference book do it. But I went ahead and did it because I wanted to program this and be able to vary my results, and so that you could see it. This is one equation that you're going to see in MATLAB in a minute. Actually, I call it A1 in MATLAB. And the other equation, after doing bunches of two tedious elimination with these two ugly equations, is that you'll get that A2 equals 1 over L R I0 plus V0. And I don't know why, but I felt like doing all of that tedious work and deriving that, because I think that we should all be able to know where everything came from rather than taking the equations right from the end. So that's the second equation that that's the second coefficient of our final solution for the current, which is right here. So that is the current in the loop. And we know what S1 is, and we know what S2 is, and now we know what A2 is, and we know what A1 is. So we now have the solution fully defined. The question is really, the question is actually comes down to the nature of these roots S1 and S2, and where they fall in under these different conditions. So let's show an example for the first case, for the overdamped case. So in summary, we found the solution to this differential equation right here, which results from applying KVL around a series RCL circuit. So the unknown is the current. The solution to that second order differential equation is a current, which it has this exponential form. And these exponents, S1 and S2, are found by the R, L, and C values. That's this is them right there. S1 and S2 are the two roots. And we often write this in a shorter hand notation of S1 equals, and this will become apparent why, S1 equals these functions of alpha, where alpha is this value and omega naught is this value here. Just quick thing, oops. Other part of my summary right here is defining out these values of alpha, and sometimes it's written alpha as alpha in S1 and S2, the two roots are written in terms of an alpha and beta, where beta is this, which the omega naught is embedded in there. So S1 and S2 are called natural frequencies, and we'll see why in a few minutes. And omega naught is called a resonant frequency. And the alpha is a damping factor, which we will also see why when we look especially at this underdamped case. You'll see what happens. So, so that was the summary right there of these equations, which are this solution applies for the overdamped case, and that's where alpha is greater than omega 0, which implies that the capacitor value is greater than this quantity 4L divided by R squared. So next we should look at an example, because this was just a lot of math and derivations. It's actually more derivations than your textbook had, and so feeling a little math heavy right now, but that's okay. I always like deriving where everything comes from. So here's my example. I have a series RLC circuit, so we know what the differential equation form for that differential equation is without re-deriving it again. So it says determine the current transient, or the transient response to this switch, and what they mean is at time 0 minus, this switch is open right here, and then at time 0 this switch closes, and the initial charge on this capacitor will go out into the circuit. So I have a current definition in this direction, which was consistent with our second order differential equation. But actually, when this switch closes, the actual direction of electron flow will be this way, but by conventional current flow, which is what your textbook has been doing all along, the current will discharge in the other direction in the circuit. So that's going to make a negative sign come out in the answer. Well, the current will go negative, opposite to this convention showing here. Okay, so R, L, and C are these values. Now it also says that the initial charge on the capacitor is given in terms of coulombs. So do recall that the initial charge, therefore, the initial voltage, therefore, on the capacitor will be the total charge divided by the capacitance in farads. Yeah, capacitance actually. Capacitance, not to confuse that with coulombs. So that's in coulombs, and that's in farads down here. So we can use that fact to determine the initial voltage, which relates to the initial charge and the capacitance on this capacitor. So V0 will equal Q over C. So you'll get the initial voltage. And notice I have I0 in my example, no initial current, so no storage of magnetic energy in this inductor right now. So this is a little, I chose to do this with a math program because actually going through and calculating all those little values was time consuming or prone to errors in my case. So so I programmed it in MATLAB, and I keep encouraging this MATLAB for you. So I created a function, the function of the time, the RLC values, the initial charges right here. I computed alpha, I computed beta. Root 1 is minus alpha plus beta. Root 2 is minus alpha minus beta. So I know I have A's and B's, but those are alphas and betas. And then I found the coefficients, the A1, A2 right here, which was that big long derivation that I did, showing you all the ugly math. not all of it because I didn't show you how I solved for two equations on two unknowns, but there's the two coefficients. And finally I have an expression for what current is, A1 e to the S1t, A2 e to the S2t. So I made this function, I call it iLoop, I store it, so it's a function that I can call in my, oh, how do you do that? So just in case you're starting to use MATLAB, you have to say new function, create a function in this function window and save it, and when you save it, it saves over here and you can see it. And so in the command window is where I can use this function. So I'm going to go back to the command window, and the first thing that I did, this is me playing around with everything, but the first thing I have to do is create an array of time, because I want to do a plot, so I want to plot a bunch of time points on the x-axis and then current on the y-axis. So you have to create, in MATLAB, you have to create all your time points that you then want to plug into the equation. So I created right here all my time points right there. So I said my time is going to go between 0 seconds and 0.15 seconds, and I'm going to go in increments of 0.0001. So that creates over here an array of time, and you can actually click in your workspace and see my time values that I'm going to plug into the equation. So right there it's 151 points that I created. Okay, so and then the next thing I have to do is say compute the y values, so I call my function iLoop right there. Remember that was my function right there, and I calculate, put in the values that I want. Here's my R, here's my L, here's my capacitor, and it turns out that capacitance, I could have put capacitance divided by or charge divided by capacitance there, but it turns out to be 200, so I just put the 200 in there. So so that calls my function, and then the last thing I do is plot. So this answer right here is an array of all the answers. I look at it right here. These are all my current values being plotted or calculated. So the last thing I just have left to do is plot this. So I actually did two cases. Ignore my little arrow down there. So because our next example that we're going to look is the critically damped one, but let's just look at right now our overdamped case. So so what I want is just to plot time against answer. Actually, I call it answer C for answer. Answer O for overdamped. And well, answer O for overdamped. Come on. Well, it's got a little compromised in my plot. I'll show it to you here in a minute. But oh, okay. So basically, come on, I can't see it. Here. I'll bring it back. So if I push the up arrow, I can see things that I just, this one. Okay. So answer O is I call the function to compute current. I give my T array right here. Here's my resistor, inductor. There's my capacitor value. There's my initial current of being 0. And here is right here the given initial charge divided by capacitance right here, which gives me initial voltage on the capacitor. So I calculate that, and now I want to do my plot. I want to plot T against the answer for overdamped, and I do that, and I'll show you the plot. There it is. So you notice that the current goes in a negative direction, which means it's opposite to the direction I've drawn, and it goes back to 0. This is a matter of convention, so I can really actually do the same. I can reverse the current of direction of current flow, or my convention, just if I want to, just to make it plot a little nicer. So I did that. And so here is the result. I have time on the horizontal axis, and this is my value of my current on the vertical axis. So current is initially 0 at the instant the switch is closed, and the capacitor quickly discharges, and the current reaches some maximum in the circuit, but now my voltage, my source, which is from the capacitor, is going down, and current decays in the circuit. So this is called an overdamped case. Now let me show you the critically damped case. So for critically damped, I'm actually only going to change the value of the capacitor, I believe. I just changed the value of this capacitor to 10 microfarads. So if I change this only to 10 microfarads here, then I will actually get the example of being critically damped. And so critically damped occurs when the alpha equals the omega naught. So let me just show you what that plot looks like, and then we'll look a little bit at what the solution is for the critically damped case. So I just changed this capacitor right here to 10 microfarads. It's going to give me the critically damped case. I'm going to go over back to my MATLAB program. The critically damped case will be, call the function with the same values in it, but change everything to 10 microfarads from 13 to get my critically damped case. Run that in. So this is going to be the critically damped case. Change that to a C. Run that and plot it again. So it's hard to see the difference. It's a very similar looking plot. The current maximum is higher here, but to see the difference, I'm going to go ahead and plot the two of them together, because then you can see the difference. So MATLAB allows you to do that. MATLAB is a nice tool. So here I plot the two of them together, and I have the minus sign in both of them just because I like my plot to go positive going instead of negative going. But that's just a matter of my current convention. So I'll plot the two of them together, show you the result. Okay, so the overdamped case is right here, and the current does not reach its current maximum. So it's the blue line. And in the critically damped case, my current can reach a higher value. So the current maximum is higher, and then also notice that the decay is quicker. So let me show you now what the solution general form is. I'm not going to go through all of the derivations this time, but it's going to be the same process. You're going to assume a solution of exponential form. You substitute it back in. You apply initial conditions to the circuit, and you get a final solution. There is a small catch for the critically damped case, which I'm going to show you here in a moment. So I like this picture, so I think I'll keep it for a minute and show you. Then I'll show you the math behind, a little bit of the math behind the critically damped case, and then we'll go to the underdamped case. So a little bit about the critically damped case. That's when alpha equals omega naught. The roots are still the same, but since alpha equals omega naught, you can see that there's only actually one solution for the root s, which will be alpha. And then you get the second order differential equation now looks like that. And just to show you, we use the same process. We start by assuming a solution of the form a e to the st. You substitute it back into the differential equation, and here it is, me doing the math right there. But what you find out is that there is only one, well, there are two roots, but they are both equal to the second order differential equation. And I'm not going to go through the derivation right now because I'll do it on a later video. I like deriving things and where they come from, so I will do it. But just in the interest of getting you to what you need to do for your homework, when you have this case, a critically damped case, the solution will end up looking like this form. So because it's a second order differential equation, you still have to have two initial conditions, and you still have these two unknown coefficients A1 and A2 that will be found from your initial conditions. So then I went back, summarized my two cases here. It's the same series RLC circuit, two different capacitor values. One gives you the overdamped case in the blue line, and one gives you the red case, which was the critically damped case, with that being the math behind the critically damped case. Now let's look at the other very interesting case, which I actually think it is the most interesting one, which is the underdamped or oscillatory case. And this will be a very interesting circuit, so let's go on to it. So this is the underdamped case where alpha is less than omega naught. Yeah. You're fine. Okay, so this is the undamped case where alpha is less than omega naught. The equation for the roots, S1 and S2, are the same, but because of this relationship where alpha is less than omega naught, the quantity under the radical is now negative, which means we have a complex root. So we rewrite that often defining yet a new term of omega sub d, which means the damping frequency, and our original omega sub 0, omega naught, is called the undamped natural frequency. And as I mentioned before, we don't want to confuse the i's and j's, so in the engineering world, the square root of -1 is given the symbol j instead of I, so that we don't confuse it with current. And then this is the natural damping frequency, which is also a natural frequency. And so these are my roots S1 and S2. It actually has the exact same solution form to the differential equation. It's just that now S1 and S2 are complex. So this looks exactly like the solution form of our overdamped case. Two distinct roots, but they happen to be complex, and two distinct coefficients that are obtained from the initial conditions. So I can rewrite that equation that way, pulling out the real part here, which causes an attenuation, and then pulling out the imaginary part right here. So kind of hard to work with it at this point, so we next want to apply, there it is repeated, we apply Euler's identity to it. So just generically written here, and we do some algebra with the coefficients, and we get the final form of the solution for the current. This is the transient current when the switch is closed and the circuit has some initial conditions on it, no source in the circuit. So this is the final solution in all real quantities that we can see a real current behavior. So this is attenuation here. You can see this is going to cause a decay, and these two the sine and cosine, is going to cause an oscillatory behavior. So for the undamped case, we need that C is less than this quantity. So I'm going to go back to the same MATLAB program that I wrote with real component values in it. I still have my R being 200 ohms, my L being 0.1 Henry, but now I lowered my capacitor value. At critically damped, at overdamped, my capacitor was 13.33 microfarads. At critically damped, I'm at 10 microfarads, and at underdamped response, I'm going to lower the capacitor value so I get a complex root there for S1 and S2. So I lowered it to 5 microfarads, and then I plotted all three. And so when I plot all three, here's the result. Make it bigger here because I'm going to play some games with the values. So here's the result. The blue was underdamped, the red was critically damped, and the yellow here, or golden color, is the underdamped case. And so what you see is that there's a big overshoot here. This overshoot is going to be an important aspect. Beyond the max current, you get this overshoot beyond the max current, and you get a dip, an actual reverse of the current flow direction here, and you start to have a little bit of an oscillatory behavior. So let me play with the values. I think it's fun to play with the values. I'm going to lower my capacitor quite a bit more in the undamped case. How about we lower it to 0.1 microfarad? So we'll do that. We'll lower it to 0.1 microfarad, and we'll see what this plot looks like now. So now we get quite a bit of oscillatory behavior, and you can see a great big huge overshoot too occurring in this underdamped. The reason it's called underdamped is because this oscillatory behavior kicks in. So that's rather underdamped. So I'm going to do it one more time, get something in between. Instead of 0.1 microfarads, let's just say 1, because we went from 5 down to 1. Look at my plot again. That's a pretty nice plot. So red is critically damped, blue is underdamped, and yellow is, blue is overdamped, so there's no oscillatory behavior, and yellow is underdamped. So underdamped is going to have an overshoot and an oscillatory behavior associated with it. So here's the three conditions plotted together. You can see in each case I just changed the capacitor value until I had the overdamped, the critical, and the underdamped conditions. Critical is also called critical because it's right on the edge of before you start obtaining the oscillatory behavior. The only other last thing to point out here is on this oscillatory behavior, it has a, you can see there, it has a kind of a period or frequency associated with it, which between, if I look at zero crossings right here, between here and here, that period, that's the damped period right there, which equals omega is 2 pi f, so omega damped, or 1 over 2 pi omega damped. So that gives you that 2 pi over, that's not quite right, that time period. Do my math right. Okay, sorry, waste your time here. So yes, that's 2 pi omega damping. Remember that omega equals 2 pi f. So omega is in radians per second, but frequency is in inverse seconds. Okay, so those are the three cases. Yeah, I think you are equipped to start your homework now, which will be out. Okay, more later. Bye now.